All right, hello again. This is Jeff Scott. Welcome to the final of my 34 tapes that I've made for Data Dimensions for discussing different facets of the Microsoft Security Development Lifecycle, or SDL. I am going to talk about buffer overflows in just a minute, but before I do, I want to put this out here one more time that my YouTube channel is right here, and I know that's kind of a lot to remember. So if you go out to youtube.com and you search for Blackhawk Technical College IT Web Software Developer, very quickly just going to show you both of these. So there is the channel right there. You can see there's a bunch of them. There's some of the ones so there's a playlist out there. So when you go there and you go to playlist, Data Dimensions. All right, it says there's 34 videos there right now, so this is the 34th or the 35th, I don't know. The other way, again, that you can get there is you can just go out to youtube.com and you can search for Blackhawk Technical College IT Web Software Developer, and it'll get you to the same place. It says right now there are 627 total videos on there. Okay, so let's get started. Get in slideshow mode here. All right. So there's about 90 slides here, so I'm going to take my time, but first we'll go over a little bit of an introduction, some definitions, definition of a buffer overflow, both the definition from Microsoft and the one from OWASP. Then we'll look at program memory a little bit. From there we'll go into the steps that need to happen for a buffer overflow to take place. We'll look at a simple buffer overflow demonstration and finally talk about 10 different methods that collectively will help prevent buffer overflows. So buffer overflows aren't new. The first buffer overflow came in 27 years ago with a Morris worm. So if you want a little bit more, you can go and click the URL. All right, but as it says, 27 years later, they're still around. In fact, as recently as May of 2015, there was a buffer overflow that was found in a Linux driver, as mentioned here, that potentially left millions of home and small office routers vulnerable to attack. So, a buffer overflow really is a simple bug. You know this as well as I do. Computers operate on data, all right? And that data, once it's waiting to be operated on, will be allocated a block of memory that's known as a buffer. So a buffer overflow happens when you try to shove 10 pounds worth into a 5-pound bag. In other words, you try to either read more data from a buffer than the buffer will hold, or you try to write more data to a buffer than the buffer will hold. So let's take a look quick. This is a two-part definition from Microsoft. They say that a buffer overflow attack is an attack in which a malicious user exploits an unchecked buffer in a program and then overwrites that code with their own data. So in other words, what they attempt to do is to take over control of the program via taking control of the machine, or vice versa. So if the program code is overridden, as mentioned right there, if the program code is overridden, the effect will be to change the program's operation. In other words, the attacker will take control over the program and make it do whatever it is they want it to do. In the best case, really, the effect would be that the program would crash. And the reason that I say that that's the best case, all right, the reason that I say that that is the best case is that if the user takes control and the program doesn't crash, the user then has control. All right, OWASP has got a little bit more information on it. A buffer overflow condition exists when a program attempts to put more data in a buffer that can hold. Okay. A buffer, again, is a scratch pad or a section of memory allocated to anything that is needed in a program. So writing outside of the bounds of that buffer can corrupt data, crash the program, or again, in the worst case, can cause the execution of malicious code that has been provided from someone else. All right, so if we look at a computer from a high level, any computer typically or really consists of a CPU, the brain of the computer, all right, which executes all the instructions, memory, all right, typically we refer to memory as RAM, non-volatile storage, so a hard drive or whatever, and I/O devices, printers, keyboards, etc. The CPU does hold a number of registers. Registers, as mentioned right here, are 16 or 32-bit high-speed storage locations that are designed for high-speed access. There's basically 4 types of registers. There are data registers, segment registers, index registers, and control registers. And to look at each one very quickly, data registers, as mentioned there, are used for arithmetic and data movement. They can be either 16 or 32-bit. Segment registers are used as base locations for program instructions. All references to memory involve a segment register used as a base location. We'll look at that in just a bit too. Index registers, as mentioned there, contain the offsets of data and instructions. An offset is how far something is from something else. And control registers, as mentioned, the instruction pointer always contains the offset of the next instruction to be executed. So that's the key thing when you're working with when you're working with a buffer overflow, is the attacker is trying to manipulate this instruction pointer so that rather than the next instruction of the code that's supposed to be executed, they can determine what instruction will indeed be executed. There's 2 basic types of buffer overflows. The major type that you hear about most often involves overwriting or changing security-sensitive variables in an unchecked buffer. This is a stack overflow. And as mentioned, it involves overwriting function pointers. It can be used to change program flow. In other words, what that would do is it would let the attacker go in and start to change the execution of the program so that rather than it executing in its straightforward manner the way it was supposed to be done, they meaning the attacker, can take control now and have it execute the instructions they want it to execute or in the order that they want it to execute. With a stack overflow, as mentioned there, the program attempts to use more space than is available on the call stack, which causes a buffer overflow. There's also a less common heap overflow. We'll talk about the difference between stack and heap in just a minute. But that involves dynamic memory location. So typically if you're working with C, for example, and you use malloc, which is memory allocate, or calloc, all right, for memory allocation. With a heap overflow, as it says, heap memory is dynamically allocated by the app at runtime, and it contains program data. So if this data can be corrupted, it causes an application to overwrite internal structures. Kind of more of the same, to be honest with you. So if you imagine program memory looks like this, and let's work our way from the bottom up. So you've got a text area which holds your program code. It's also called the code segment. You've got your static data area in here which holds both your initialized and your uninitialized data. So you've got a data area and a similar area to it that we'll get to in just a minute. Then you've got your heap data area and your stack data area. And notice the address is here. Start low and go up. Stack data area starts high and goes down. So the text area, again, is mentioned. It's named the code segment. It's read-only. So it's an area of memory so that if you've got several users using the same system, they're able to run their executables concurrently without having to worry about anyone breaking in, so to speak, in this case, and having a buffer overflow exploit, because this is the read-only program code that's in a binary format. All right, as mentioned here, any attempt to write into it will result in a memory access violation and a program termination. Next is the data and what's called the BSS, or basic service set segments, which contain global variables. Global meaning they're available program-wide. The main difference between these segments is that the data segment contains variables which have been initialized, whereas the BSS holds global variables that have not been initialized. And as I go through this, I like to, when I think that it'll help in understanding, so sorry about that. Next, again, is the heap data area. The heap data area, again, is above but adjacent to this static data area. All right, and as mentioned there, this particular area is allocated at runtime, typically by the C language malloc and calloc, and I put links to both of those, and the C++ new operator. Again, it grows from a lower address to a higher one. The heap is mentioned similar to a C pointer because it doesn't exactly hold data. Rather, it holds another memory address to where that data is. Okay. Finally, we have the stack area. The stack is a LIFO, or last in, first out area. It grows down from a higher memory address to a lower memory address. And as mentioned previously, it's like a computer scratch pad. So it holds data temporarily. All right. As well as, and this is the important part, the address for the next instruction to be executed. All right, this return address, as it says, represents executable code sitting on the stack waiting for its turn to execute. Now, in order to really understand this stuff, you need to understand the stack, you need to understand registers and how they function, all right, before you understand how a buffer exploit can be done. So this is a 5-step process right here. So first, a buffer overflow vulnerability must be found, discovered, or identified. There's 4 ways that can be done. Somebody else can find a potential problem and report it. The user or somebody can scrutinize the source code and try to find it. Sometimes you find it, as it says there, by accident or sheer luck, but most often with attackers, they find it by brute force or brute trial and error. So next, after the vulnerability has been found, the size of the buffer must be determined. This is typically done through experimentation. So you try to throw input at the program, and eventually you hope that it crashes. After you figure out the number of characters it takes to crash the program, you can move on to step 3, where the attacker must be able to control the data that's written into the buffer. And again, you're going to see an example of this in just a minute. All right, that's the example that we'll go through in just a couple minutes. Number 4, there must be security-sensitive variables or executable program instructions that are stored below the buffer in memory. Attempting to overwrite this, all right, by overflowing the buffer with user input will affect the program outcome. Finally, whatever was in there in the buffer area must be able to be replaced with other executable instructions. So as we look at this, you'll notice that what we have in here is we have 3 character arrays. One that's called name, 8 bytes, one that's called etc underscore password, 8 bytes, and one that's called password, that's 8 bytes. We tell the user to enter their name, then to enter their password, and you notice both of these use gets. Gets is an inherently flawed C function. All right, so it's possible to stuff more in there than you should be able to stuff in there. Then you print the 2 out. All right. Then, as it says, we call the authenticate function. What that does is it's got our 2 8-character buffers and attempts to copy whatever we passed in for the name into buffer 1, whatever we passed in for the whatever we passed in for the password into buffer 1, and then whatever is in that file, in the password file, for buffer 2. And if it's in there, we call permit. So in other words, it's valid. But there are some inherent problems with this. First, as mentioned here, this is a very simplistic example. You'd typically put more checks in here than this, but I wanted to be able to show you something as far as how this works. So again, we've allocated our 3 character array variables. We then request that the user input their name and password. We use the gets function. Next, we authenticate, or attempt to authenticate, using the string copy function, which is also flawed. Finally, we use the string compare function, which is also flawed, to compare the contents of the 2 buffers. If they match, as it says, the user is authorized and is permitted to use the system. So in an ideal world, you do something like this. Username Mark, notice that's less than 8 characters. Password PASSWD, again, less than 8 characters. So it says the password is passed, etc. And it says, okay, this is the password we put in. We found that in our file there is a password that is named that, so the user was successfully authenticated. Good. So there doesn't appear to be a problem. All right. So what is the problem? Well, we begin to feed varying length input into the program's password request. Eventually, we hit a point where we have discovered a vulnerability. And we get something like this. Now, this shouldn't be thought of by the attacker as a bad thing. This is a good thing. All right, we've caused a buffer overflow to happen. So what we need to do is we need to determine exactly what that point was in the system where we are no longer able to put in code without blowing the system up, so to speak. In other words, what's the max number of characters we can put into the buffer legally? In this case, it's an 8-character array. So we can put in 7 characters plus our \0, which is our null terminator. So we know at the point that the buffer begins to overflow. So step 2 has been completed. Remember, we're an attacker doing this, so we don't have access to this source code. So now that we know that it'll hold up to 7, we feed 10 X's in there and see what happens. So as you can see, for the password, we put in 10 X's. All right, so buffer 1 and buffer 2 aren't even the same right here. So now the next thing we have to do is we have to attempt to overwrite a security-sensitive variable by overflowing the vulnerable buffer. So notice what we have in here. Mark, and then we've got password, which was all okay, 2 X's, so that's 8. Then we put the word phony in there. All right. So it says the password is password, PASSWD. All right. The name and the entries were Mark and password phony. Well, we can already tell that buffer 1 and buffer 2 are not the same. So as it says, what we've done is we've changed the system password from password to phony by overwriting it. So now we, as the hacker, have control over the program. Typically, though, to a hacker, just getting control over the program isn't going to be enough. They're looking for a bigger exploit. They want to become root or administrator. Again, the goal of the hacker is to obtain elevated system privileges. this is what they're going to be able to do. So again, working our way up from what we've seen before. All right. So again, we had our data segment in here, our text segment, our data segment. We worked our way up to our heap, and we worked our way up eventually to the stack. We have successfully completed a buffer overflow. So it didn't seem very hard, so what do we do to prevent this thing from happening? So in the next several slides, we're going to see 10 different yet related preventative measures, all right, including using different program language tools. Well, as time has gotten on, as the old saying goes, the mice have gotten smarter, so we've attempted to build better mousetraps. Still, there's problems with that because most libraries that are written eventually go down to be written in C. Microsoft, as mentioned, has completely rewritten Visual Basic and Visual C++ with string-safe security in mind. And they've added some Visual C# tools from the ground up with security in mind. Number 2, eliminate the use of flawed library functions. We already talked about string copy. We talked about string compare. We talked about gets. Those are the 3 that were used in the demo that we just went over. Again, you can see that I have hyperlinks if you want more about those. We could have eliminated the buffer overflow by just changing this line. So instead of saying this, string copy, which does no checking, we use strncopy, that's the number, and we tell it once you've reached 8 characters, don't do any more copying. That's exactly what it says right here. It must discontinue the raw copy after 8 bytes. All right. In an earlier lecture, we talked about the 100 or so banned C functions, and if you forgot that, there's the URL for it. Third, we can design and build security within our code. It takes more time and effort, but it has to be done. So we could have added one extra step to assure complete buffer safety. And that is, when we do our string copy, instead of putting an 8 in there, we can say the size of buffer 2, which means that make it just big enough to hold whatever the size of buffer 2 is, plus the null termination character. As it mentions here, this typically goes back to how programmers are trained. Is code security taught and encouraged? Are programmers given the extra time to design security within their code? Are programmers given time to go to security training? All these are typically no. 4, use safe library modules. We've talked about the fact that Microsoft has created their own string class to do bounds checking. All right, and as mentioned there are string safe library modules available for many languages. 5, use available middleware libraries, which offer some more safety involved, and I put a URL into some of this. 6, use source code scanning tools. As mentioned here, attempts have been made to design tools to perform analysis on raw source code to try to identify problematic areas where buffer overflow vulnerabilities exist. In another URL. There are compiler enhancement tools that you can use, such as Stack Shield. As mentioned here, Stack Shield is a tool to protect programs from buffer overflow attacks, but they don't change any of the code. Stack Guard, which is a similar product. All right, as it says, it protects the return address from the stack from being altered. Going along with that, you can disable stack execution. So as mentioned, there are patches available. Most of these are Unix-based that render a stack non-executable. Since most buffer exploits depend on an executable stack, making this modification will essentially stop them from happening. Know what's on your system. All right. Be aware of who has privileges and what they can execute. Find them, list them, know them, have them documented someplace. Finally, patch the operating system and the application. So stay informed, remain offensive. So to summarize, and I kept it real simple, Buffer overflows have been around for years. They'll continue to exist as long as there are programmers. They may never be eliminated, but they can be at least somewhat mitigated.